Where are the alien encounters if there are any? If alien life exists, it may be as simple as bacteria or more complicated than humans, and there are effective methods for finding both. Enrico Fermi, a famous physicist, is credited with asking the question, "Where are they?" in response to his surprise at the lack of any evidence for the existence of extraterrestrial intelligent civilizations in the Milky Way galaxy. There is no agreement on which, if any, of the numerous potential solutions to this so-called Fermi paradox is true, despite the fact that many have been put forth over the years. However, one of the most fascinating issues in science in general and astronomy in particular continues to be whether or not we are alone in the Milky Way, or in the entire universe. We will make an effort to briefly identify the most general, remotely detectable signatures of extraterrestrial life, both simple and intelligent, and to examine the expected efficacy of different search strategies. This is due to the enormous uncertainties surrounding the emergence, evolution, and survivability of any extrasolar life, if it exists. This subject has gained particular relevance because observations, primarily from the Kepler Space Telescope, have revealed that there are billions of Earth-sized planets in the Milky Way that orbit Sun-like, or smaller, stars in the Goldilocks region, where liquid water can exist on the planet's surface. This region is known as the habitable zone. The $100 million, 10-year Breakthrough Listen project has significantly advanced the hunt for extraterrestrial intelligent life. It does this by looking for extraterrestrial communications in the electromagnetic spectrum between 100 MHz and 50 GHz. Nearly as soon as the planet cooled enough to sustain water-based life, simple life began to emerge on it. However, for life to be remotely detectable, it must have advanced to the point where it dominates the planetary surface chemistry and has dramatically altered the atmosphere, leaving behind chemical biosignatures that can be recognized in theory. For example, it is likely that Earth itself would not have been discovered as a planet capable of supporting life during the first 2 billion years of its existence. The primary unanswered questions about the development of intelligent life are as follows. What geochemical limitations exist on the development of sophisticated life? What timelines do those restrictions require? Are there evolutionary filters or bottlenecks that make the leap to intelligence extraordinarily difficult? For instance, it took roughly 3 billion years for the earliest multicellular life forms to emerge on Earth. Even the most basic kind of interstellar communication, radio reception and transmission, took 4.5 billion years to develop, along with numerous other factors like plate tectonics and asteroid collisions. The importance of initially determining if planetary systems older than the Solar System are typical in the Milky Way is illustrated by these factors. According to a recent study that looked at the history of planet formation, the Solar System formed close to the median epoch for large planet formation, and roughly 80% of the planets that are currently known to exist as being Earth-like may have already been formed at the time that Earth was formed. We now have a lot of leverage to investigate intelligent life beyond our solar system. Which visible biosignature, on a sufficiently old, rocky planet, in the habitable zone, may be regarded as the most dependable for the existence of basic life? The most promising initial aim would presumably be an atmosphere that is highly rich in oxygen, say, 20% or more, even though no single biosignature would be completely persuasive. While non-biological mechanisms, such the splitting of carbon dioxide by strong ultraviolet radiation, are capable of producing oxygen in a planetary atmosphere, these rarely occasionally result in such high levels of enrichment. The likelihood of an oxygen-based origin would, however, only be greatly increased in conjunction with other putative biosignatures, such as methane. In light of this, searching for oxygen would be a great starting point in the very near future while attempting to support it with additional biosignatures in the search for simple extrasolar life signals. If these are outfitted with very high dispersion spectrographs, this can, in theory, be accomplished with large, ground-based arrays of relatively inexpensive flux collector telescopes, such as a next-generation European extremely large telescope, with a collecting area the size of a few football fields. It would therefore be necessary to do the more challenging infrared methane detection. What would a space mission need to accomplish its goals? If such a mission fails to find any biosignatures, we would like to be able to at least set a meaningful constraint on the rarity of extrasolar life. A mission contender for the 2030s would be the more ambitious 9 to 12 meter large UV, optical, IR, LUVOIR type space telescope, such as the projected high-definition space telescope. In an ideal world, one would look beyond biosignatures to find the most direct evidence of an extraterrestrial technological civilization. The goal of the SETI Search for Extraterrestrial Intelligence program may be the unmistakable detection of an intelligent, extraterrestrial signal, most notably by radio transmission. However, it's possible that an advanced life form would view radio communication as antiquated. Its use may have been transient in the majority of civilizations, making it uncommon across a substantial portion of the cosmos. So what could a generic signature be? An advanced civilization is characterized by high energy use, which is almost impossible to hide. More pessimistically, biologically based intelligence might only be a relatively short stage in the evolution of complexity, followed by the singularity, the supremacy of artificial, inorganic intelligence. If this is the case, the most advanced organisms are unlikely to be found on a planet's surface, where gravity is both beneficial and detrimental to the evolution of biological life. But due to energy considerations, it is likely that they are still close to a fuel source, specifically a star. Even if such sophisticated devices were to convey a signal, our relatively inept organic brains would likely be unable to recognize and decode it. If this scenario is accurate, finding simple life by biosignatures may be much more likely than finding clever ETs. However, the most exciting possibility still revolves around the ultimate objective of identifying the hallmark of a sophisticated intellect, whether it be biological or non-biological. All power to 2020 initiatives like NASA's Far Infrared Surveyor and Japan's Space Infrared Telescope for Cosmology and Astrophysics, SPICA. The important thing to remember is that, for the first time in human history, we won't be able to genuinely respond to the question, "Are we alone?" for another 2 or 3 decades. The relevance of the response cannot be overstated because it may have a significant impact on our final assertion that we are unique in the universe.